Welcome to lecture 7.4 on geometrically defined vectors and applications. We're going to look at some basic terminology first. We're looking at the scalar. This is the magnitude of a quantity. It can be represented by a real number. What we're talking about here is when you're scaling up or scaling down. For example, if you wanted to double the size of something, you would multiply it by a real number, the real number 2, right? You would double it. And that's what scalar. If you wanted to cut something in half or scale it down, the number would be 1/2, okay, or 0.5. A vector in a plane is just a directed line segment. You might also heard it called a ray. It's also used to denote a vector. So here's an example of one. Here you have the vector OP. It can be written with capital letters OP or the capital letters with a ray on top of them. O is called the initial point. You see where it's beginning, and P is the terminal point where it ends, or the direction it's going to, and you can see that with the arrow. Magnitude is simply the length of a vector. This is expressed as the absolute value of OP. We say that two vectors are equal if and only if they have the exact same magnitude or length, and they're going in the exact same direction. So they would be, if you saw them, they would be parallel. They would be parallel. Here we have vector OP and vector PO. These are not equal, although they're the same magnitude. They are going in opposite directions. Okay. So here's some examples of equal vectors and some unequal vectors. So you can see that A and B are equal vectors because they are the same magnitude, they're parallel, heading in the same direction. Similar with vector C and vector D. Vector E is the same magnitude as vector A, but you can see that it's going in an opposite direction, so they would eventually have a intersection point, which is definitely telling you that they are not the same or equal. And then vector F is going in the same direction as A, but it's not the same length. You can see it's a bit shorter. The sum of two vectors is also a vector if we add two vectors together. And that vector sum, for example, vector A plus vector B, would end in what's called the resultant vector. Okay, there's two ways to do this. You can, if we're trying to add vector A and vector B, you can put the beginning of vector B at the end of vector A, and then the vector that connects the beginning of the first vector and the end of the second vector, you can see is that resultant vector. Okay. You can also start both vectors A and B at the same origin point, initial point. And you can see that here that their initial points are an intersection piece. And then by building a parallelogram whose diagonal is then the resultant vector A plus B. Okay. So we can draw these as a parallelogram. We can also draw these as a triangle. And we'll look at some examples of cases for both. The sum of a vector and its opposite vector has magnitude 0 and is called the zero vector. Okay. At the bottom here you can see if we had vector B and we added the opposite of B, or what you might think of as negative B, you could see that we would get back to this origin point and just be at the point, and that's why its magnitude is 0. If we want to subtract a vector from another vector, we can do this by adding the negative vector, which is the same thing we could do with normal addition and subtraction. Again, you see this here. If we wanted A minus B, we would take the vector A We can see the vector b here with the same origin point, and we would do negative b in the opposite direction, the same magnitude, and then build the parallelogram. And so this is the resultant for a minus b or a plus negative b. Scalars we mentioned before with the vocabulary. The scalar product of is just a real number and a vector. And it's simply the vector, you multiply the scalar times the magnitude of the vector, and it's going in the same direction. This is pretty logical, right? So if we had u, you can see is this black vector. If we had 2u, then it would be going in the same direction, but it would be twice as large. 3/2 u is 1.5 times as large. Half u is half the size of the vector u. And you can see that those three vectors are all going in exactly the same direction. They're all parallel. Negative 2u is, again, double the vector magnitude, which you can see here. It's the same size as 2u. But of course, then if the direction changes, it's going to go in exactly the opposite direction. Most of this is pretty intuitive. So I think that you won't have a hard time kind of sorting this out on problems. So let's talk about some old geometry specifically related to parallelograms, because we're going to use this to solve some triangles and some problems. Remember, a parallelogram is a quadrilateral whose opposite sides are parallel. Okay? Opposite sides and opposite angles of a parallelogram are equal. The opposite sides are equal, the opposite angles are equal. And the angles that are adjacent to each other, the angles that are next to each other, are supplementary. Remember, that means they add up to 180 degrees. If you draw the diagonals of a parallelogram, they will bisect each other, meaning that they will cut each other in equal lengths. You know, you'll have half, at the intersection point, you'll have half the length of each diagonal. But they do not necessarily bisect the angles. So you cannot count on that if you draw a diagonal, that the angle is cut in half. You cannot count on that. It may be true, it may not. So you cannot use that as a rule to solve triangles or any of the problems. Diagonals do not necessarily bisect the angles. They bisect the diagonals. So let's try a problem. We have two forces of 15 and 22 newtons. Here we can see the 15 force. This is the vector PQ. The vector PS, we can see, is labeled at 22. Notice the power or the force is what we call the magnitude of the vector. Okay. Newton specifically is a unit of force that equals 0.225 pounds, almost a quarter of a pound. If the angle between the two forces is 100 degrees, you can see that here. Find the magnitude of the resultant vector. Remember that we find the resultant vector by drawing the parallelogram and then building a diagonal across from the origin point or the initial point of both of the vectors. Okay, so we're trying to find the magnitude of vector v, this diagonal in the parallelogram. We know that opposite sides are equal, so we have 15 and 22. We know opposite angles are equal, so this angle R would also be 100 degrees. And we know that angles that are adjacent or next to each other are supplemental or add up to 180 degrees. Since this angle is 100 given in the problem, this corner here would be 80 degrees in the upper right, angle Q. And of course, because it's opposite angle S, these two angles are also equal. Okay, a diagram on all of these problems is really important, so that you can visualize it and then you can figure out the relationships between angles, etc. We've got this already. So we can use the law of cosines to solve either of the triangles. We have side, angle, side. So the magnitude of v squared is, remember this is the law of cosines, is the square of both the sum of the other sides, so 22 squared plus 15 squared minus 2 times the product of the other sides, 2 times 22 times 15 times the cosine of the angle between them. Okay. If we do the math here with your calculator, we get that v squared equals 594. Taking the square root, we get 24. So the magnitude of the resultant vector is about 24 newtons. Okay. So everything that we needed to do to solve this problem was to be able to visualize it, to build it, knowing what a resultant vector is and how to create it, building a parallelogram, and then knowing the properties of the parallelogram. Sometimes it's necessary to find a vector that will counterbalance a resultant. This just simply means that it's going to be like the opposite of that vector, okay? So the opposite vector is called an equilibrium. The equilibrium of vector u is the vector opposite of u or negative u, okay? So let's look at a problem here. Finding the magnitude and direction of an equilibrium. Find the magnitude of the equilibrium of forces of 48. Here we've actually drawn these together at an initial point. So we have a little bit different. Oh no, this is the same. What am I saying? Sorry about that. Here, the initial point of the first vector is vector AB, and we can see that with 48 newtons. Vector A something else, we can see labeled as 60 newtons. And we know that the angle between them is 50 degrees. Again, we build a parallelogram. The diagonal is then the resultant vector. And we want the equilibrium, which is the opposite of the resultant vector that's in this diagram, is negative v. Okay? So we're looking for the magnitude of negative v. Okay? And also, then we're looking for the angle between the equilibrium and the 48 Newton force. Well, here's the equilibrium, and there's the 48 Newton force. And so we're actually looking for this angle, which is alpha. Okay, we're looking for angle alpha. So again, we have side, angle, side, side, angle, side. So we can figure out the magnitude of vector v, the resultant, by simply using the law of cosines. Okay, just like we did in the last problem. Okay, so we do that, 48 squared plus 60 squared, etc. We get 9606. We take the square root and we get 98 newtons. The magnitude of the equilibrium is the same as the magnitude of the resultant. We do not give sizes in negative numbers, so be careful, okay? So the negative here indicates the direction it's going, not the value of the magnitude. The magnitude of the equilibrium is not negative 98. It is 98. It's the same size. It's just going in the opposite direction. So be careful with that, okay? We think of the equilibrium as the opposite of the resultant, but it doesn't mean it has a negative magnitude, all right? The required angle alpha can be found by subtracting angle CAB Where is CAB? CAB, right? From 180. Now be careful. This is the part I was saying, it looks like, that diagonal of the resultant splits that angle in half, right? And so then that seems like it would make it a really easy problem, 180 minus 25. But we don't know that it does that, so we cannot assume that half of that angle is there from the diagonal. We have to figure out what this angle A, we need to figure out what the angle CAB is, like whatever that little part of A above the resultant is. We need to know that for sure, and we can use the law of sines to find that. Okay, the sine of CAB over its opposite, 60, is equal to the sine of 130 over the vector, which is, of course, 98. Okay, remember the sine of an angle over its opposite, the trig function sine of an angle divided by its side length is equal to another angle in the triangle divided by its side length. Okay, so we have this. We've done a number of these. I'm not going to walk through this too slowly. So the sine of CAB is equal to 60 sine 130 over 98, which is 0.469. We take the inverse sine, and we get that CAB is approximately 28 degrees. This is a great problem to kind of really raise our awareness that this diagonal does not cut that angle in half. It's not 25 and 25. Our angle is actually 28. So pay close attention to that. Okay, so now we've answered the problem. The equilibrant has a magnitude of 98, and the angle between those two, the equilibrant and the 48 Newton force, is 152 degrees. Okay. These are really quite common. Inclined plane problems are very common in trigonometry, and we're going to go through a lot of things on this slide that are kind of building your base knowledge, and I'm going to start with what I want you to get from this. Okay, let's first look at the verbiage here. Find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal. So there's the ramp. It's got a 20-degree incline, etc. Okay, and all these are problems. We assume there is no friction. Friction creates a whole nother mathematical issue. Okay, notice that the vertical force represents the force of gravity or of the weight, 50 pounds, okay? Your weight is just a function of gravity, okay? This will always be the case. Dropping down a perpendicular bisector to the ground will represent gravity or the weight of an object, okay? We can see that from what we've just learned, that BA is equivalent to BC plus negative AC. That's just what we've learned about vectors and resultants. Okay. Vector BC represents the force with which the weight pushes against the ramp. Your weight is based on gravity, which is a direct perpendicular force to the earth. Here, since we're on a hill, there's a different value of that weight, as we've seen, caused by the angles and the trig functions. It's not going to be the same magnitude. It's going to be slightly smaller. Okay. Vector BF represents, BF is this little red vector right underneath the top tire, represents the force that would pull the weight up the ramp, that would pull the wagon up the ramp, okay? Vectors BF and AC are equal, okay? This will always be the case, okay? The vector needed to pull something up the ramp will be equal to this opposite triangular side that connects the force of gravity directly down perpendicular to the earth with the force of the weight on the inclined plane. Okay? These will always be equal. This force to pull it up the incline will always be equal to the force here, or the side of this inclined triangle. All right? Vectors BF and AC are parallel, so the measure of angle EBD, this is the actual inclined plane, equals the measure of angle A. EBD equals the measure of angle A. Okay? EBD, angle A. Okay? This is alternate interior angles. Parallel, alternate interior angles. Okay? Since that angle A and sort of the angle B are equal, angle D and angle C are both right angles, we have similar triangles. And so that means the other angles are equal as well. And this is the big thing. Specifically, the measure of the inclined plane is equal to the measure of this angle between the force of the gravity and the force of weight on the inclined plane, and that will always be the case. Okay? When you're solving these inclined plane problems, you'll be drawing this special triangle here and solving for it. So knowing that this triangle here is similar to this inclined triangle, that these angles are the same, is vitally important, and that this perpendicular down represents the weight of the object. Okay, so that was a lot to tell you to get you those kind of two fundamental facts, that we're going to always be drawing this triangle to solve forces on an inclined plane, that the angle of the incline is equal to this angle at the top, and that the weight will be the perpendicular dropped ray or vector. Okay, so with that we can see that the sine of 20 is equal to AC over 50, right? This is AC is here over 50. The sine, we have a right triangle, so sine equals opposite over hypotenuse. The sine of 20 equals the opposite, AC, the size of that, over the hypotenuse, which is BA, which is the weight. So we get that side AC, or the magnitude of AC, is approximately 17. So a force of approximately 17 pounds will keep the wagon from sliding down the ramp. The idea here is that if it takes, if it takes 17 to pull it up the ramp, then we have to have an equal force going the opposite direction to keep it in motion, or to keep it out of motion, excuse me, to keep it stable. Okay? You might want to review this again, but really what I want to remind you is this angle, 20, of the incline is going to be the angle of the triangle here. We're going to be building right triangles, so we can use our basic trig function, SOHCAHTOA, to solve. And the perpendicular line vector that we drop down to the earth is the weight of the object. So remember those for solving these problems. Okay, a force of 16 pounds is required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? So again, we've labeled the 40 pounds, the weight. We've labeled the force needed to hold that mower in place. And we need to figure out what the incline here is going to be. Okay, right? What is the angle of the incline? We know that this angle equals the angle ABC, this top angle here. We see that we have the opposite side and we have the hypotenuse, and so we can use again the sine function to find this. Okay, so the sine of angle B in this blue triangle here is equal to the opposite 16 over the hypotenuse 40, which gives us 0.4, and the inverse sine gives us an angle of 23.6 degrees. Okay, what they're mentioning here is just the stuff that I really emphasized on the last slide, that works the same for all incline problems. Okay. So the hill needs to make an angle of about 23.6 degrees with the horizontal in order for that amount of force of 16 pounds to hold the mower in place. All right. A ship leaves port on a bearing of 28 degrees and travels 8.2 miles. The ship then turns due east and travels 4.3 miles. How far is the ship from the port and what is its bearing? You have to draw it. You have to draw it. So it's very important that you understand how to do bearings. Remember, there were two ways to do bearings. You had just a straight bearing, which was measured clockwise from the direction north, or you had a north by east, north by west, south by east, south by west bearing. Okay, so this first bearing, when it leaves port, it's going 28 degrees from the north and going for 8.2 miles. That would be its magnitude. Then it's going to turn due east. Well, this is just putting another compass mark here, the cross, and going due east, which is directly to the right along that compass mark line, and it'll go 4.3 miles. Okay, how far is the ship from port? That is the resultant from the original starting point to the ending point, and what is the bearing from port would be the angle of north to that resultant. See if you can draw it. I want you to hit pause and see if you can draw it. Hit pause now so that you can check your diagram first. It's very important that you can draw these things. So try drawing it and then hit play again. All right, so here's our diagram. Let's walk through it. 28 degrees. We start at a north angle and go 28 degrees to clockwise, and we can see that's our vector there, PA. Okay, port to our first stop A. Okay, and we can see the magnitude is 8.2 miles. It then goes due east. So this is another point. I would have actually drawn a cross here and then gone directly to the right, etc. And this is 4.3 miles. Now, how do they know that this is 118 degrees? Notice that we are seeking the magnitude of the red line, the resultant PE, and we're also trying to figure out what the angle is from this north arrow all the way to that red PE vector. Okay? Since this triangle is a right triangle, NAP, we know that this angle is 90, so we can find the angle NAP, which is 62 degrees. Okay? And that's how we figure out that this is 118. 28 plus 90 plus 62 equals 180, which is the sum of three angles in a triangle. And then, of course, a straight line, angles are supplementary. They have to add up to 180, and 62 plus 118 adds up to 180. And so that's how we get the angle inside of here. Notice now that we have side, angle, side, we can solve for this triangle. Okay? We can solve for this other angle here, and then add it to 28 to find our bearing. and we can solve for this other side here as well. So first, let's use the law of cosines to solve for the magnitude of PE, which is our distance from port. Side squared plus side squared minus 2 times the product of those sides times the cosine of the angle between them. PE squared equals 118, so PE equals approximately 10.9 miles. Okay. Bearing is again NPE, so let's find again this measure APE using the law of sines. So the sine of this little angle we're looking for, the sine of that angle over 4.3 is equal to the sine of 118 over that magnitude we just found, which is 10.9. Okay, the sine of APE over 4.3, the length of its side opposite, is equal to sine 118 over the magnitude of its side opposite, which we just figured out as 10.9. Solving this, we get that angle APE is 20.4. Be careful, that's not the end. That's just this interior angle here. We want the bearing, so now we have to add 28 degrees to that, and to find out that the bearing is 48.4 degrees. Okay. The key well, there's a lot of knowledge built into this, but the key is being able to draw these diagrams, especially with bearing, etc. Okay. These problems with airspeed and ground speed can be very confusing. Okay. These are also about building a vector and resultant. So you need to understand how this works. So the airspeed of a plane is its speed relative to the air. Okay. The ground speed of a plane is its speed relative to the ground. Okay. You might think of airspeed as, let me rephrase that. You think of ground speed as the speed of the actual plane in relationship to the Earth. Where is it going? Because we always measure things relative to the Earth. What's happening with airspeed is, in order to go a certain speed relative to the Earth, let's say between LA and San Francisco, you want to travel, relatively along a line that's on the Earth between those two cities. But the wind is blowing, and so if you just try to fly along that line, the wind is going to blow you off course. The wind is going to blow you off course. Okay, so pilots will fly at a different bearing that takes into consideration of the wind speed and direction. And if you've ever, bicycled or canoed or something on a windy day, you know how easy it is to get off course. You're heading your canoe relative to the Earth in a certain direction, but the wind, you might have thought of it as the wave or your bicycle. The wind is pushing your bike or whatever vehicle you're in off a little bit. Okay, so let's look at this diagram. Here is the bearing and the airspeed. This is where the plane would actually take off from and head this direction, knowing the wind direction and speed is going to act on the plane. And so the ultimate direction the plane is going to go is this resultant in green, which is actually the course of the plane and the ground speed of the plane. This is the actual direction it's flying. Okay, so airspeed and bearing plus wind speed and bearing give us the actual direction and course of the plane and its ground speed, the speed it's traveling relative to the Earth. Okay, I know that was a lot, but I wanted to go through that slowly. Airspeed plus wind direction give us course and ground speed. An airplane that is following a bearing of 239 degrees, remember, start at north, go clockwise 239 degrees, at an airspeed of 425 miles per hour, that's your magnitude of that vector, encounters a wind blowing at 36 miles per hour, your magnitude of the wind vector, from, very key word here, from a direction of 115 degrees. So we're almost talking about adding a negative vector, the opposite direction of the wind or something. It's coming from 115. So make sure you pay attention to that. Okay? Find the resultant bearing and ground speed of the plane. Again, you need to draw this. So take it a stab at drawing this. It's one simple sum of two vectors, the airspeed and the wind speed, and finding the resultant, which would be the course and ground speed. So hit pause again and try drawing it. All right. So let's see what we have here. So notice we first start off with the airplane is following a bearing of 239 degrees. We start at north and go 239 degrees, which take us into quadrant 3. It's on this bearing, and the magnitude of, or the speed of the plane is 425, so we've labeled that. Okay? The wind now acts on this vector from a direction of 115 degrees. So again, we have the compass here. We go 115 degrees clockwise, and we get this vector here. But this is the direction it's coming from. So it's starting here and going toward vector 2. Okay, toward vector 2. All right? We've labeled some other angles in here that we would know. For example, if it goes 115 for this wind vector, then we know that in quadrant 4, this little angle is, I just went blank, sorry. This little angle is 25 degrees, 115 minus 90. And then, of course, this little angle with this red vector and the y or x-axis negative is also going to be 25 because it's a vertical angle. We didn't label that. We can see this angle here is going to be 59 degrees. That might help us as well. And let's see what we can figure out. Of course, the ground speed is the resultant vector, and bearing is this vector b here. That's the resultant of these, the airspeed of the plane and bearing, and then the speed of the actual wind. Okay. All right. So B is what we're trying to figure out. Notice angle A. Notice angle A is the angle we're trying to find. That's the bearing. No, sorry, that's 239. We are trying to find that 239 plus alpha, right? That'll give us the bearing of, and then we're trying to find the magnitude of angle of side B, vector B. All right. Vector C represents the airspeed and bearing. Vector A represents the speed and direction of the wind. Angle ABC has its measure the sum ABC. Where's ABC? ABC has its measure the sum of angle ABN. ABN, this is that north angle. And N1BC. So it's this angle here. If you think of B as the angle for this triangle, then it's angle B. All right. SAB. SAB measures 59 degrees. We can see that because it's 239 minus 180, north to south. Okay. ABN1. ABN1 is also, that's this interior angle to the right of the north, this little inside angle, because these are alternate interior angles. This is parallel lines. They're being cut by a transversal. This is what we learned in chapter 1 or 2. So this angle here is equal to the right side of the north, you know, about a little bit, about half of that angle. It's not half exactly. Okay. All right. Angle E1BF, E1BF. This angle here is equal to 115 minus 90, that's the 25. Thus, angle CBW1 also measures 25. I've already mentioned that. And so this angle, because this is equal to 25, then this side of the north inside there, this side of the angle B represents 90. That's the quadrant 2 measure, minus that 25 measure, which is 65. So on the left side of this north axis, we have 65 degrees. On the right side, we have 59. And so the total of this angle B is 124 degrees. Okay? You can see how important it is to be able to identify angle measures and how they relate to each other. You might want to go back and look at alternate interior angles and, when two parallel lines are crossed by a transversal. So now that we have some of the angles here measured out, let's go ahead and find the resulting bearing and AC, as well as the ground speed of the plane. Okay. Sorry I had to go on to a second page. I don't like that, but I didn't have much choice there. Okay. So I did add in here that the angle ABC, that was the one we just figured out, is 124 degrees. Kind of like angle B, really. All right. So we have side angle side now. We can easily find the length of the third side using the law of cosines. Okay. B squared equals A squared plus C squared, etc. Plugging in all the values, we get B squared equals 199,000, and so B equals approximately 446 miles per hour. To find the bearing of B, we need to find angle alpha, that's this little one inside the triangle, and then add the 239 that goes all the way to the airspeed. Okay, so the sine of alpha over 36, the sine of this angle over the side opposite, is equal to the sine of 124 over the length of the side opposite, which we just found, 446. So the sine of alpha equals 36 sine 124 over 446. And so we take the inverse sine and we get 4 degrees. So alpha is 4 degrees, thus our bearing is 243 degrees. So this plane is flying at a ground speed of 446 miles per hour on a bearing of 243 degrees relative to